Hey everybody, so this is the third time for me trying to record the Respiratory Volumes lecture after spending 47 minutes on the phone waiting for Apple and being hung up on, and then waiting another 23 minutes on the phone and finally connecting to somebody. I have the microphone on my iPad now working again. I have no idea why it stopped working or why you would ever want it to stop working, but it's working again. And so we're going to go over the respiratory volumes. I sure hope to God that this records this time. So just want to bring up this slide cover here. So respiratory volumes are just the amount of air that can be inhaled, exhaled, or remain in the lungs. So basically we're quantifying different amounts of air that are in the lungs at different points in time. And these volumes have clinical utility. That's why we bother differentiating between them, giving them rather elaborate names, is because we can analyze these lung volumes and be able to make certain types of prognoses as far as patient outcomes are concerned with them. So the respiratory volumes are measured, and by the way, respiratory volumes are the same thing as lung volumes. When we say lung volumes, we're saying respiratory volumes. When we're saying respiratory volumes, we're saying lung volumes. So these respiratory volumes are measured in pulmonary function labs, which are usually within the context of a hospital. Within these labs, respiratory therapists perform pulmonary function tests. And these tests make use of a device called a spirometer, which is, It makes use of a device called a spirometer, which is basically measuring the speed of airflow, and then a computer attached to the spirometer extrapolates these different volumes based on that speed of air that passes through the spirometer. Spirometer basically is hooked up to a hose through which the patient is inhaling or exhaling through. So let's talk about the tidal volume, the most important of these respiratory volumes. The tidal volume is simply the amount of air that's inhaled or exhaled with each normal breath at resting conditions. And the tidal volume is about 500 milliliters. So you can think about the tidal volume in the context of inhaling, inhale 500 milliliters, or you can think about the tidal volume in terms of exhaling, exhale 500 milliliters. In either way, whether you're talking about inhaling or exhaling, you're still talking about the tidal volume, and it's still 500 milliliters. So let me introduce you this concept here on this graph that we have in front of ourselves. And now this graph is more of kind of like a combination of a chart and a graph. So the chart part of it are these different multicolored blocks. And this is not the best color scheme. It's not the color scheme I would have chosen because most of the colored blocks are like different colors of blue. And so they kind of blend together. They don't really stand out. But okay, this is what we have. This is what's in your book. And these different colored blocks are supposed to represent different lung volumes. Now, they are tied to the graph. It's more important that you understand the graph. So first, when reviewing the graph, let's go over the axes. So the y-axis is the amount of gas, or amount of air, rather, more specifically, that's in your lungs at any given time. And it's in milliliters. Now, you could convert the milliliters to liters very quickly, right? And that's just a matter of shifting the decimal point 3 places to the left. So, for example, we have a maximum amount of 6,000 milliliters that can fill up these lungs that we're talking about. 6,000 milliliters would be the same as 6 liters. So I may interchangeably go between liters and milliliters, but it's all the same. We're just talking about the volume of air in the lungs at any given time. The y-axis is going to be time. And more specifically, it's going to be time in terms of seconds. So this is a fast-moving graph if you were to see it in action. The black line here represents the amount of air that's actually in the lungs at any given time. So right here, where we start at time 0, we have about 2,500 milliliters or 2.5 liters of air in the lungs. And then we are going to inhale a tidal volume, which is about 500 milliliters, to bring up a grand total of 3,000 milliliters, or about 3 liters in the lung. And then we are going to exhale that same tidal volume here, and that takes us back to roughly 2,500 or 2.5 liters of air within the lungs as a whole. So that's tidal volume. It's no more complex than that. Now let's talk about Inspiratory Reserve Volume, your IRV. Your Inspiratory Reserve Volume is the amount of air that can be forcefully inhaled after a normal tidal volume inspiration. So let's start right here. Our baseline is having about 2,500 milliliters of air in the lungs, and then we inhale a normal tidal volume, which takes us up to here. So now we have 3,000 milliliters of air in the lung. And then this is our new baseline. This is our new zero. From this point, we inhale as much as we possibly can. And these are big lungs, so we were able to then take in a total of 6,000 milliliters or 6 liters of air into the lungs. Now, remember, the place from which we started was when we already had 3,000 milliliters of air in the lungs. So when you add another 3,000 milliliters, that's what takes you up to the 6,000 milliliters. So that additional 3,000 that you inhale, that additional 3,000 milliliters of air that you inhaled, that is your Inspiratory Reserve Volume, IRV. Okay. And by the way, let's go back to the blocks. Remember I told you these blocks correlate with these different volumes. So this powder blue block, right, which I'm isolating right here, is going to be tied to these tidal volumes, which can be either measured with inhalation or exhalation. And then in contrast, the Inspiratory Reserve Volume is encompassed by this large kind of shale-colored blue block right here. That amount of air which you can inhale after inhaling a normal tidal volume. So the Expiratory Reserve Volume is basically the opposite of the Inspiratory Reserve Volume. The Expiratory Reserve Volume, in order to model that, I'm going to get rid of this curve, pretend that doesn't exist, and pretend from here we're just going along with nice, easy tidal volume. So we inhale a normal tidal volume, and then now we're going to exhale a normal tidal volume, and then stop. That's our baseline, where we have about 2,500 milliliters in the lung. And then from this baseline, this new zero, we exhale as much as we possibly can. And it turns out here, for demonstration purposes, we're going to say this Expiratory Reserve Volume is 1,200 milliliters. Don't get hung up on the numbers, by the way. The numbers are not important, except for maybe the tidal volume. Tidal volume is important to know that is about 500 milliliters. But to know that the Expiratory Reserve Volume is 1,200 milliliters is not that important because it changes. It varies based on the individual. And that's always a number that you'll be able to appreciate when you're doing these pulmonary function tests. So in any event, you exhale a certain amount of air. It happens to be 1,200 milliliters. So if you take 1,200 subtracted from 25, which was where you started with your baseline, that's going to take you down to about 1,300. So it must be right here that we now have a grand total of 1,300 milliliters in the lungs, right? So that is our Expiratory Reserve Volume. So again, everything in this darker shale blue bar is going to be our, or represent our Expiratory Reserve Volume. That the volume represented by this blue bar is our Expiratory Reserve Volume, is a better way to say it. Okay, so residual volume, also sometimes referred to as the reserve volume in some textbooks. I remember way back when I first learned about it, I learned about it as the reserve volume. Our textbook calls it the residual volume. So the residual volume is just this volume of air represented by the green block. This is the amount of air that's in the lungs that can never be forced out. So when you think about how our lungs are constructed, you have your secondary bronchi, you have your tertiary bronchi, you have all of the bronchi splitting and splitting and splitting and splitting down to the level of the bronchioles, and the bronchioles continue to split and split and split and split until you finally get to the terminal bronchioles, and then you have additional air passageways of the respiratory zone after that in the alveoli. So you got a lot of air-filled spaces within the lungs. You never want to evacuate all of the air from those spaces, because if you did, you'd have a full vacuum and the lungs would collapse in on themselves, right? So there always has to be a certain amount of air that's always in the lungs, and that's represented by this residual volume, which here it's actually 1,200, but really I just realized that someone did their math wrong. It really should be 1,300. But again, don't get hung up on the numbers. The numbers are not really what's critically important here. The important thing is the concept. Okay, so now let's look at the respiratory capacities or respiration capacities. This is just simply when you take two or more lung volumes and add them together. And the reason that we have respiratory capacities is because they have certain clinical prognoses to them, all right? We can be able to predict patient outcomes based on our measurement of them, all right? Or possibly by measuring them over a long period of time, we can further gain information about what's this patient's likely prognosis, how will the disease progress, is the disease getting better, et cetera, et cetera. All right. In a nutshell, they're useful. All right. That's the reason we teach you them, because they're useful. So now these brackets represent the additions of these multiple respiratory volumes, which are represented by the multicolored blocks, right? So these brackets that encompass multiple multicolored blocks represent these respiratory capacities. So the first respiratory capacity we're going to talk about is probably the more minor of the respiratory capacities. This is called the inspiratory capacity. So the inspiratory capacity is simply just your TV plus your IRV. So it's the powder blue bar plus the light shale blue bar all together gives you your inspiratory capacity. Inspiratory capacity, if you wanted to measure the inspiratory capacity, you'd ask the patient to exhale a normal tidal volume, and that would take them here to this baseline where they have about 2,500 milliliters of air in their lungs. And then from that point, that's your new baseline. You ask them to inhale as much as they possibly can, and that's their inspiratory capacity. Now, the functional residual capacity is going to be the combination of the expiratory reserve volume, your ERV, plus your residual volume. So this is represented by this bracket right here. So the darker shale blue bar plus the lime green bar equals your functional residual capacity. Now remember, did I mention this? Well, if I didn't mention this, then I'm going to mention it again. The residual volume can never actually be directly measured in the context of pulmonary function tests. Now, they can measure it, but usually you have to send a patient off to a more sophisticated lab, and it's seldomly ever done. Oftentimes it involves having the patient inhale radioactive gas within a sealed box and all this kind of weird stuff. It's stuff that you don't really want to have to do to a patient unless you really, really need to. And there are certain types of restrictive airway diseases where the pulmonist may want to order this test, but it's seldomly done. So under normal circumstances, we just estimate the residual volume. It's just estimated, and it can be estimated based on weight, height, age, etc., stuff like that. So given that we can only estimate the residual volume, you can only also estimate the functional residual capacity. There's no way that you can actually definitively know the functional residual capacity if there's no way that you can definitively know the residual volume. Okay, so vital capacity. Vital capacity is the most clinically significant of all of these respiratory capacities. So the vital capacity is a combination of your inspiratory reserve volume, tidal volume, and your expiratory reserve volume, as symbolized by this large bracket right here. So the way that you would measure the patient's vital capacity is that you would ask them from their baseline after taking a normal exhale tidal volume, you then ask them to inhale an inspiratory capacity, and then once they have the maximum amount of air they can in their lungs, you ask them to exhale as much as they possibly can until they feel sick. Now, a lot of times in the pulmonary function test, the respiratory therapists have to ask the patient to perform this test multiple times because patient compliance is an issue. People don't want to have to exhale as much as they possibly can until they feel uncomfortable, especially if they have different types of chronic lung diseases like COPD, which we talked about before. Okay, so total lung capacity is very easy. This is just the combination of the inspiratory reserve volume, tidal volume, expiratory reserve volume, and residual volumes. You add them all up together, and that's our grand total of 6,000 in the case of this person, 6,000 milliliters of air that can be totally stored within the lungs. Okay, so rates of gas movement. So sometimes it's not only beneficial to know about the actual volumes of gas in the lungs at any given time, but we may also want to measure the rates in which gases are going into or out of the lungs throughout a certain duration of time. And that duration of time is usually a minute, and that's what these two measurements of the rate of gas movement are measured in terms of 1 minute. So we're going to talk about, first of all, the minute respiratory volume, or MRV, is the amount of air that flows into or out of the respiratory tract in 1 minute. It doesn't matter whether you're talking about the amount that flows in or out, because the amount that flows in or out is going to be the same over the course of a minute. And I'll show you what I mean by that right now. So in order to calculate the MRV, you start with the TV, the tidal volume. That's the amount of air that you can either inhale or exhale under normal circumstances, normal resting conditions. And then you just multiply that number times the number of breaths that occur in 1 minute. right? That's your respiratory rate, right? Which is usually like, 16 to 18 breaths per minute. So if you multiply the amount of times that you take in or exhale a normal tidal volume in 1 minute, then you get the amount of total air that you either inhaled or exhaled within 1 minute. And again, it doesn't matter whether you take it from the perspective of inhaling or exhaling. You just got to choose one. If you calculated your tidal volume through inhaling, fine, good for you. Then that's what you go with. If you calculated your tidal volume through exhaling, fine, good for you. That's what you go with. It doesn't matter. But in the end, you just take your TV and you multiply it times the amount of breaths per minute, or your respiratory rate. Now, keep in mind here, the unit for the frequency is breaths per minute, and then the unit for the TV is going to be milliliters. As a result, the total unit that you get for the MRV is going to be milliliters per minute. And anytime you measure something per unit time, you are taking a rate. Okay, so the next concept I need to go over is important for the next measurement of the rate of gas movement, which we're going to talk about. It's also the last one we're going to talk about. So dead space, or anatomic dead space, is just the amount of air that's trapped in the conducting zones. So if you guys remember the conducting zones in the lungs, that's your secondary bronchi, tertiary bronchi, your bronchi derived from the tertiary bronchi, your bronchioles, all the way down to your terminal bronchioles. Those air passageways are kind of analogous to the ducts in the heating system in your house. There is no gas exchange going on, all right, between the air in the passage and the walls of the passageway. Right, so basically the air is just hanging out there. It's just kind of in transit. Right, it's between locations, but there is no diffusion of the gases going on there. And so from a physiological point of view, we're really not interested in that air, because at that given time in which it occupies the anatomic dead zone, or the conducting airways, it's not doing anything for us. So in order to take a more specific measurement of our MRV, all right, a sub-measurement of our MRV, we're going to want to subtract out that dead space. So basically, as a rule of thumb, when you consider the tidal volume, for every 500 milliliters of tidal volume you inhale or exhale, about only 150 milliliters of that actually is just exclusively contained within your anatomic dead space. So in order to figure out the amount of air that we inhale or exhale that actually comes into direct contact with the alveoli where diffusion is occurring, we just subtract the amount of air in the anatomic dead space from the tidal volume. And we use this number to then multiply times the frequency of breaths, or inhalations or exhalations, and that gives us this new, more precise term for measuring the rate of gas movement, which is known as your ARV, your alveolar ventilation rate. This is the amount of gas in the amount of air in 1 minute that comes in direct contact with your alveoli. So again, in order to do this, you take your TV, right, which is about 500 milliliters usually, and you subtract your anatomic dead space, which is usually going to be about 150 milliliters or so. And then that resulting number you multiply times the breaths per minute, your respiratory rate, and that gives you your alveolar ventilation rate, which is still taken in the same units, because the units over here have not changed at all. All right, so